last lecture we had started discussing about the inverted Wishart distribution, and we had proved an important result that if A has got a Wishart distribution, Wishart m n sigma, sigma is positive definite, then expectation of A inverse was defined to be the inverted Wishart distribution. So, expectation of A inverse was equal to sigma inverse that divided by n minus m minus 1. Now, we will use this particular result that we had derived in the last lecture in order to get to an unbiased estimator of sigma inverse when we have a random sampling from a multivariate normal distribution. That is, suppose we have got the following setup. Suppose we have x1, x2, xn, a random sample from a multivariate normal distribution with a mean vector mu and a covariance matrix sigma, then what is an unbiased estimator of the sigma inverse matrix? As one can feel that it's basically going to be based on this particular result that we had derived. Now, what do we know when we have a random sampling x1, x2, xn from a multivariate normal distribution which is given by multivariate normal m mu sigma? Sigma of course is a positive definite matrix. Then we know that n minus 1 s, let me still write it as Sn minus 1 to indicate that this is the sample variance covariance matrix with a divisor n minus 1. This is given by I equal to 1 to up to n xi minus x bar into xi minus x bar, its transpose. And this we had seen from the result proved in the last lecture that this has got a Wishart distribution on m dimension with n minus 1 degrees of freedom and an associated variance covariance matrix as sigma. So, this would imply by this result out here that expectation of the inverse of this Wishart matrix, that is expectation of n minus 1 is n minus 1 inverse of this, because we require expectation of the inverse of the Wishart matrix, that is the inverted Wishart. This would be given by sigma inverse whatever is the associated variance covariance matrix. Here the associated variance covariance matrix is sigma. So, this divided by, we had here n minus m minus 1. So, n is the degrees of freedom of the Wishart distribution, here that is n minus 1. So, that we will have this as n minus 1, this minus m minus 1. So, that this is equal to sigma inverse this divided by n minus m minus 2. So, this would imply further that this expectation of, now we have here inverse of this quantity. So, we will have s n minus 1 inverse of it, that divided by n minus 1, this is equal to this sigma inverse divided by n minus m minus 2. And what does that lead us to? This would imply that expectation of this n minus m minus 2, what we have on the right hand side, that divided by n minus 1 times s n minus 1 inverse, that is equal to sigma inverse. So, this would imply further that this n minus m minus 2, that divided by n minus 1, this constant multiplier times Sn minus 1 inverse matrix is an unbiased estimator of sigma inverse. So, we have the desired quantity, that we have obtained a matrix which gives us, which is an unbiased estimator of the sigma inverse matrix. So, that is a simple result. Now, we move on to Hoteling's t-square distribution, which is the multivariate generalization of the student's t distribution for the univariate setup, Hoteling's t-square distribution. Let me first give the definition of what a Hoteling's t-square distribution is. Suppose we have got a Wishart distribution, suppose S follows a Wishart distribution, Wishart M n sigma, and D be a random. Now this S of course is any random matrix which is of the order that it is m by m, and let D be a random vector m by 1 which has got a multivariate normal distribution, multivariate normal m dimensional with a mean vector as say delta vector, and a covariance matrix given by C inverse sigma, where C is a scalar constant. C is a scalar constant, and suppose we further have S and D are independently distributed. These two are independently distributed. Then Hoteling's t-square distribution is defined in the following way. Hoteling's t-square is defined as t-square, which is equal to C times n times d prime S inverse D. Now this is what is the Hoteling's t-square Hoteling's t-square statistic. Hoteling's t-square on n degrees of freedom. So this has got a Hoteling's t-square distribution on n degrees of freedom. The degrees of freedom, what we have here, n, is associated with the degrees of freedom of the associated Wishart distribution, which comes as a constituent part of this Hoteling's t-square distribution. Now the thing to be noted here is that we are just looking at two sets of random variable. One is a random matrix, another one is a random vector, and we have a Wishart distribution of the random matrix, and we have a multivariate normal distribution of the random vector, and critically we would require independence of this random matrix S and this random vector D. Now the Hoteling's t-square distribution of course is a very important distribution in multivariate distribution theory. As I said that this Hoteling's t-square is the generalization of the usual student's t-distribution in case of an univariate distribution. So this is going to solve, or rather this is going to be used in problems similar to what we had used say a student's t-distribution in case of univariate normal distribution theory. But before we can use that, let me just try to look at what is going to be the distribution of this t-square statistic. So in order to get to the distribution of t, what we do is we go in two steps in order to get to the distribution. Now first observe that given D, we will have this distribution D prime sigma inverse D, this divided by D prime S inverse D. Now this is a quantity which we had introduced in the last lecture, and we know that this has got a central chi-square distribution on n minus m minus 1 degrees of freedom, and is independent of this D vector. We had derived this particular distribution taking it first as a conditional distribution, because once we say that observe that given D, that is conditioned on D being a given vector, we will have the distribution of this to be a central chi-square on n minus m minus 1 degrees of freedom, and that is independent of D. It does not depend on the particular choice of fixing of D, and hence the unconditional distribution, which is this D prime sigma inverse D divided by D prime S inverse D, has got a chi-square distribution on n minus m minus 1, a central chi-square distribution. Now further, we have this D random vector to have a multivariate normal distribution, multivariate normal M delta. C is a scalar constant, remember, C inverse sigma. Now, from the results of the quadratic forms associated with a multivariate normal distribution, what we can say is the following, that this d prime C inverse sigma, this is the covariance matrix, inverse of that multiplied by d, this is going to have what distribution? This is a quadratic form in D. So, this will have a non-central chi-square, a chi-prime square on the degrees of freedom. Degrees of freedom would be the full of this particular matrix. So, it's the degrees of freedom is m, and a non-centrality parameter, say, that is given by tau square. So, this is a non-central chi-square on m degrees of freedom, and with a non-centrality parameter, tau square. And what is that tau square? The tau square term is going to be given by delta prime C prime sigma, the inverse of it, that multiplied by this delta. That is, in other words, this non-centrality parameter here is just C times C, a constant, scalar constant, delta prime sigma inverse delta. Now, this quantity here, this random variable, is going to have a central chi-square distribution if we have this tau square to be equal to 0. Only under that particular condition this will have a central chi-square distribution. Now, an important thing to note here at this particular point is that we have the distribution of this to have a chi-square distribution, which is independent of this d, the random vector, which is having a multivariate normal distribution. Now, using that random vector d, which is having a multivariate normal distribution here, the quadratic form what we have here has got a chi-square distribution, a non-central chi-square. Now, whatever be that, the important thing is that since this quantity here is independent of d, and so will be this independent of the quantity with which we have obtained this non-central chi-square. So, what can we say? This will imply that this d prime, then we have that inverse of that quantity, which is C sigma inverse d, that was the term there, is independent of the term which we had first defined, that is d prime sigma inverse d, that divided by d prime S inverse d. Why is that so? Because this is based on that d vector, which is independent of this quantity, which is having a central chi-square, and then if we have that, anything that is derived from that d vector would naturally become independent of this quantity here. Now, using that and the fact that this has got a non-central chi-square on m degrees of freedom and a non-centrality parameter as tau square, and this as a central chi-square, we can frame the following statistic. This would imply that this C d prime sigma inverse d, this is having a non-central chi-square on m degrees of freedom. So, we have this chi-square, non-central chi-square, divided by its degrees of freedom, that divided by the second chi-square, which is independent of the first chi-square critically, d prime sigma inverse d, this divided by d prime S inverse d. So, this is the second chi-square, and this divided by its degrees of freedom. What was it? It was n minus m. This is going to have a chi-square on n minus m plus 1, actually, not minus 1. This is chi-square on n minus m plus 1 degrees of freedom. So, what we have here is this n minus m plus 1 degrees of freedom. This would follow what distribution? Now, this is a chi-square random variate, a non-central chi-square random variate on m degrees of freedom. So, we have made that chi-square divided by its degrees of freedom, chi-square divided by its degrees of freedom. The two are independent. So, this will have a non-central f distribution on the degrees of freedom, which is m, n minus m plus 1, and the non-centrality parameter of this non-central F distribution would be same as the non-centrality parameter of this numerator chi-square, which is a non-central chi-square distribution. So this is a non-central F distribution on M n minus m plus 1, the 2 degrees of freedom associated with this, and a non-centrality parameter tau square. Now tau square is what we had written out here, which is C times delta prime sigma inverse delta, right. So in order to get to this statistics distribution, what we have used is the fact that this quantity here follows a chi-square on n minus m plus 1 degrees of freedom given d, and also since it is independent of the particular choice of d, the unconditional distribution of d prime sigma inverse d divided by d prime s inverse d follows a central chi-square on n minus m plus 1 degrees of freedom, and that is going to be independent of this second chi-square, which is c d prime sigma inverse d, which is a non-central chi-square. So using this central and the non-central chi-square, we frame this particular ratio, which is having a non-central F distribution on the degrees of freedom and the non-centrality parameters as given above. Now if we simplify this particular term, what we will be getting is this term cancelling out, d prime sigma inverse d. So we will have this as c d prime s inverse d, and this multiplied by n minus m plus 1, that divided by m. This follows this f prime, the non-central F distribution on m, n minus m plus 1 degrees of freedom, and the non-centrality parameter equal to tau square. Now it's easy to see that what is the relationship between this statistic and the t-square statistic. What was t-square statistic? We had defined the t-square statistic as c times n. N was the degrees of freedom of the associated Wishart distribution. So c times n d prime s inverse d. Let me go back to that particular definition. T square was defined as c n d prime s inverse d, and hence if we have obtained the distribution of this quantity, we have obtained the distribution of t square. That is, what we will be having is t square by n. T square by n would be just c times d prime s inverse d. So it's t square by m into n minus m plus 1 divided by m. This would follow that non-central F distribution m n minus m plus 1 and a non-centrality parameter as that equal to tau square. So this is the desired distribution of our Hoteling's t-square statistic. Now let us look at applications of this Hoteling's t-square statistic, applications of t-square statistic, and how, where actually this statistic is going to be used. Now suppose we have a multivariate normal distribution, say we have a multivariate normal distribution NP mu sigma, say sigma is positive definite, both this mu and sigma are unknown. So we have this particular setup. Now under such a circumstances, suppose we have a null hypothesis H naught being framed as mu equal to any specified vector mu naught. This is to be tested against an alternate hypothesis HA, which says that mu is not equal to mu naught. So this is a type of testing which we very frequently come across in multivariate theory, where we are looking at this mu vector to be tested as taking this specified value of mu naught. Mu naught vector is of course specified. So in order to test this, what we do is we take a random sample as in univariate theory. So x1, x2, xn be a random sample from this multivariate distribution, multivariate normal m mu sigma, And then we will have to use this x1, x2, xn in order to test this null hypothesis against this alternate hypothesis. What do we know about this random sampling? We know the following fact, that x bar, the sample mean vector, has got a multivariate normal distribution with a mean vector as mu and a covariance matrix as sigma by n, and about the variance covariance matrix, say this S is Sn minus 1, I'll drop this subscript n minus 1, we will say that this, wherever I have this S, it's basically denoting the sample variance covariance matrix with a divisor n minus 1. So n minus 1 S has got a Wishart distribution, Wishart m, on n minus 1 degrees of freedom and an associated variance covariance matrix as sigma. And what is more about these two statistics is that x bar and S are independent. So this is what we have already proved from concerning random sampling from a multivariate normal distribution. Now, can we use these two information in order to get to a Hoteling's t-square distribution and then frame the testing procedure for testing this null hypothesis against this alternate hypothesis? Yes, because if we look back at the definition of Hoteling's t-square, we would require a Wishart distribution, we would require a multivariate normal distribution, and we would require independence of the two. So what we have to use is the following. We may recall the theory that we have just now learnt is that if S follows Wishart m n sigma, I'll just write it once again, and this D is another random vector which is having a multivariate normal m. Let me write it in the notation that I had introduced first up. So this was a delta C inverse sigma, and if we have these two to be independent, then the Hoteling's t-square statistic was defined as C times n d prime S inverse d. So this was Hoteling's t-square on n degrees of freedom, and furthermore the quantity which was t square by n minus m plus 1 divided by m, this was shown to have a non-central chi-square on m n minus m plus 1 degrees of freedom and a non-centrality parameter equal to tau square, where this tau square is equal to C delta prime sigma inverse delta. So this is the fundamental result that we have stated today and proved a part of it about the Hoteling's t-square distribution. So we have here two constituent parts, which is this having a multivariate normal distribution and this having a Wishart distribution, and they are independent. So this falls perfectly in line with this setup. So for the random sampling, we will have the t-square statistic to be given by C times n. Now let me write that statement once again here so that it would be easy for us to see why the parameters are that. This was having a multivariate normal distribution with a mean vector mu and a covariance matrix as sigma by n, and our n minus 1 Sn minus 1 actually was having a Wishart distribution on n minus 1 degrees of freedom and an associated variance covariance matrix as sigma. So this falls in line with this particular definition. So we will have this t squared statistic being given by C times n. Now what is C here? C inverse is n inverse. So C is our n, and what is our n? N in this definition of the Hoteling's t-square is the degrees of freedom, associated with the Wishart distribution. The degrees of freedom corresponding to our multivariate normal distribution is n minus 1. So this basically is the C in this definition of Hoteling's t-square, and this is the degrees of freedom of the associated Wishart distribution, which was given by this n. Now what is d prime in our case? It is x transpose prime. X transpose prime, and this times S inverse. Now what is our S inverse? This is our, what I'll do is I'll just make this first as this quantity. This is n minus 1 S whole inverse. This is n minus 1 S whole inverse X bar, right? So this is what is the counterpart of this quantity for the random sampling here. Now this is going to have a non-central F distribution, constant multiplier of that. What I'll do is that since our null hypothesis is mu equal to mu naught, since our null hypothesis is mu equal to mu naught, now we know that if we have a null hypothesis, then we will have to look at the distribution of the test statistic under the null hypothesis, and hence we have to bring in this particular mu equal to mu naught quantity somewhere here, and that we will do out here, which is mu not equal to mu naught is the alternate hypothesis. So if we define this quantity, mu naught, remember, is a known quantity. So x bar minus mu naught, what is the distribution of this? This is going to have a multivariate normal distribution, multivariate normal M, and the mean vector would be 0 under only the null hypothesis, and the sigma by n as the covariance matrix, this under H naught. Now if that is not under H naught, then what would be the mean vector for this x bar minus mu naught statistic? It would be mu minus mu naught, because expectation of x bar would be equal to mu, and under the null hypothesis only that mu is equal to mu naught. So under the null hypothesis we will have this to be a null vector and sigma by n to be the associated covariance matrix. Nothing changes as far as the sample variance covariance matrix is concerned. We will have that to have a Wishart distribution with n minus 1 degrees of freedom and an associated variance covariance matrix sigma. So we will have this Hoteling's t-square distribution, Hoteling's t-square statistic rather, defined in terms of this new vector, which is centered in order to take care of this under the null hypothesis condition. So what we will be having here is once again C remains n, and n is the degrees of freedom, so it's n minus 1. So we will have this n into n minus 1. Then d prime would now, the role of the d prime will now be played by this x bar minus mu naught quantity. So it's x bar minus mu naught transpose, then the Wishart distribution's inverse n minus 1 S whole inverse times x bar minus mu naught. So what we see is that this n minus 1 term cancels with this one, and what we have is this n times x bar minus mu naught prime S inverse x bar minus mu naught in a neat form. Now this would further imply from the distribution of this t-square statistic that this t-square divided by n in the previous setup was the degrees of freedom, so we will have that as n minus 1, this into n. Now the role of n is played by n minus 1, so we'll have that n minus 1 minus m plus 1, that divided by m, the dimension. This would follow an F distribution, F prime distribution with degrees of freedom as m. Now what is this equal to? This is just equal to n minus m and a non-centrality parameter equal to tau square. Now this non-centrality parameter tau square, remember, was associated with the mean of the associated multivariate normal distribution. So this is a null vector here. So delta prime inverse of this particular matrix into delta would just be equal to 0, because delta, the mean vector under the null hypothesis, so tau square will be equal to 0 under the null hypothesis H naught. So we will have actually a central chi-square, a central F distribution as the null distribution. So this would imply that the t squared that we had defined, that divided by n minus 1 times, we have that as n minus 1 minus m plus 1, that divided by m. This follows a central F distribution on m, n minus m degrees of freedom under the null hypothesis H naught. So if we have that to be a central F distribution, we will use this distribution in order to reject or accept the null hypothesis. So the test for H naught against HA is to reject H naught if t square is large, that is, we will reject H naught at level alpha if our t square by n minus 1 into n minus m by m, if observed value of this test statistic exceeds fm n minus m at the tabulated value at alpha percentage point. So this becomes finally the testing procedure for testing the null hypothesis, that mu equal to mu naught against mu not equal to mu naught. So we look at the deviation x bar minus mu naught term here, and then this basically serves as the test statistic which is having an F distribution on m n minus m degrees of freedom under the null hypothesis, and hence the test is that if the observed value of this test statistic exceeds the upper alpha percent tabulated value of an F distribution on m n minus 1 degrees of freedom, we reject the null hypothesis and accept H naught otherwise. So that's the testing which we have obtained using the Hoteling's t square distribution. Now this Hoteling's t square distribution, I said to start with, is the multivariate generalization of univariate student's t distribution, and hence we will see shortly how this is generalizing or now note that if m is equal to 1, then we will basically be having a univariate distribution, because the dimensionality of the multivariate underlying multivariate distribution was m. So if we take m equal to 1, then this statistic reduces actually to a student's t statistic. Now suppose we have got m equal to 1, that is, we are looking at univariate distribution theory. Suppose we have got m equal to 1, then what happens to this particular statistic out here? It is t square. Now what was t squared? T square was given by this, okay. So this is equal to, in such a situation, given by t square by n minus 1 into n minus m divided by m. So for the value of m equal to 1, this is equal to t square by n minus 1, then this is also n minus 1 divided by 1, and hence this is just equal to t square. And what is t square equal to? T square for m equal to 1 would be, let's look back once again at the form of t square, it's n times this particular quantity here. Now we have m equal to 1, so this x bar minus mu naught is a scalar quantity, and what is S inverse? If we have m equal to 1, S is the sample variance covariance matrix. If we have univariate distribution, then this is just the sample variance. So what we will be having as t square is n times x bar minus mu naught whole square, that divided by S square, where S square is the sample variance. So this would thus be given by n times x bar minus mu naught whole square, that divided by S square. This will follow an F distribution on 1, that is m, n minus m is n minus 1 here, and this is equal to what? This is a student's t distribution square on n minus 1 degrees of freedom, right? Because an F distribution on 1 n degrees of freedom is equivalent to a t square on the same degrees of freedom. So we have got this, and note that what we have here, which is the value of the t square by n minus 1 into n minus m by m, for the special case that we have univariate theory. So this is what we have, and this, the square root of this is precisely the student's t statistic, that is what is used if we have x1, x2, xn, an univariate, a random sample from a univariate normal distribution with a mean equal to mu and an unknown variance equal to sigma square. Then the square root of this basically, or the square of that, if we have an F statistic, is what is precisely used in case of an univariate distribution theory. So this Tn minus 1 is student's t distribution on n minus 1 degrees of freedom. So this implies that this Hoteling's t square is generalization of this student's t distribution in the multivariate setup. Now the testing procedure that we had framed was for a general mu equal to mu naught against mu equal to mu naught. As a special case, one can take this mu naught to be a null vector, and in such a situation the t square statistic would just be n times x bar transpose S inverse x bar, and all other things remain exactly the same. So for any specific choice of mu naught vector, one can obtain this particular testing procedure. We will extend this Hoteling's t square distribution, or rather the testing procedure, when we have two multivariate normal population. But before that, let me just look at the following important thing, which is the relationship between this Hoteling's t square and a testing procedure which is based on the likelihood ratio principle. So the relationship between t square, the Hoteling's t square, and likelihood ratio is what is now the point of interest to us. Now suppose we have the same setup as that of the multivariate normal distribution random sampling. So this is a random sample from a multivariate normal M mu sigma. Sigma is positive definite, is unknown, and mu is also unknown. So suppose we have got this null hypothesis mu equal to a null vector. This is to be tested against the alternate hypothesis that mu is not equal to that null vector, and we can do, just now we have seen that this type of testing we can carry forward using the Hoteling's t square distribution. Now what we are now going to look at is what is the relationship of the t square statistic that we had introduced with that of the general principle of the likelihood ratio. Now in order to implement the likelihood ratio, what we would require is first the likelihood function. So let us look at this likelihood function, the likelihood function L mu sigma. This given, I just write x, x is the matrix which contains x1, x2, xn. So that's going to be given by, as we have seen earlier, 2 pi to the power minus mn by 2 determinant of sigma to the power minus n by 2, then e to the power minus half trace of sigma inverse a minus n by 2 x bar minus mu transpose sigma inverse. I don't have any place to write this here, so this is this x bar minus mu. So that's what was the form of or the simplified form of this likelihood function. So this is the constant part, 2 pi to the power minus mn by 2, then determinant of sigma to the power minus n by 2, and then this, as we had seen, perhaps it would be better if I write the first form and then write this simplified form. Well, this basically is coming from here. This exponent in the first form would be L mu sigma given x, this is going to be equal to, the constant is as it is, minus mn by 2, determinant of sigma to the power minus n by 2. So this is mn by 2, determinant of sigma to the power minus n by 2, and then in the exponent what we have to start with is minus half summation j equal to 1 to n xj minus mu transpose sigma inverse xj minus mu. And as we had seen when we were talking about sufficiency concept and the related maximum likelihood estimation, we had seen that this particular likelihood function can be conveniently written in this particular form, where A of course is this matrix, where A is the sum of squares and the cross product matrix, that is A is summation j equal to 1 to up to n xj minus this x bar into xj minus this x bar transpose this matrix, right. So if this is the likelihood function, then the likelihood ratio, before even introducing the likelihood ratio, let me look at the spaces. This mu, the null hypothesis is mu equal to mu naught. This is to be tested against the alternate hypothesis that this mu is not equal to mu naught. Now let me denote by script theta the parameter space without any restriction. So it's basically the set of all mu and sigmas such that mu belongs to r to the power m, because we have got that as m dimension, and then the sigma matrix is all possible positive definite matrices. And then we also look at this script theta naught, which is the parameter space under the null hypothesis. So the parameter space script theta naught under the null hypothesis mu h naught is going to be given by the set of all mu and sigmas, such that this mu is fixed at the null vector point and sigma is allowed to be any positive definite matrix. Now under these two parameter spaces, the likelihood ratio is defined in the following way as usual. Likelihood ratio, this lambda, is going to be given by the ratio of the two supremums. So supremum under script theta naught of this likelihood function L mu sigma. I'll just drop this conditioned on x, just to keep it as L mu sigma, that divided by supremum over the entire parameter space script theta of this likelihood function. So this is the likelihood ratio, that's what is going to be defined, and the likelihood ratio test would reject the null hypothesis h naught in favor of the alternate hypothesis HA if this likelihood ratio is small, because we are looking at the supremum of theta naught by supremum of theta. So we will have to find out what is supremum under theta naught and what is the supremum under the unrestricted supremum under the parameter space script theta. Now in order to do that, we would require actually what is the maximum likelihood estimates of the unknown parameters under the two setup. For the unrestricted setup, that is unrestricted is for script theta, we know what the maximum likelihood estimators are. The maximum likelihood estimators are the following. Maximum likelihood estimators are this mu hat is equal to x bar, and this sigma hat maximum likelihood estimator is 1 upon n times a. We had derived this particular result earlier, that these are the maximum likelihood estimators in case of a multivariate normal distribution. Now if we are looking at the supremum over script theta of this L mu sigma, then that would be obtained if we plug in these values as the corresponding maximum likelihood estimators and then see what is the form of this quantity now. So this would be the supremum of the likelihood function under script theta would be, this constants will remain as it is, and then we will have determinant of sigma hat to the power minus n by 2. So what would that be equal to? Sigma hat is going to be replaced by n inverse a to the power minus n by 2. So that's what is doing the task of this sigma hat. Then e to the power minus half trace of sigma inverse a was the term which we had in the likelihood function. It was this as trace of sigma inverse a. So what would that be equal to? Sigma is n inverse a, so sigma hat inverse by invariance of the likelihood principle would be n times a inverse. So this is n times a inverse, this is for sigma, and then we will have that A matrix coming as it is. And what happens to the second term? The second term is minus n by 2 x bar minus mu transpose sigma inverse x bar minus mu. Now at the point that mu is given the maximum likelihood point, so that would be x bar, so this term would vanish simply. So what we will be having is this term just for the supremized or rather the supremum over script theta of this likelihood function. What is this going to be equal to? A inverse A is going to be an identity matrix of order m, so the trace of that would just be nm. So that this we can write as 2 pi to the power minus mn by 2, and we can take this n inverse out from this particular determinant of n inverse A matrix, and what will happen to the power of n will get raised to the power mn by 2, because we have a negative sign here, we have a negative sign here, and the order of this A matrix is m by m. So we will have this n raised to the power mn by 2, and then we will have e to the power minus half trace of n times im, so that would be n times m, so that this is mn by 2. So this simple form is the supremum of the likelihood function at this script theta point, right? Now we have to obtain also the supremum of this likelihood function under the restriction that h naught mu equal to mu naught. So we will have to work out also that restricted MLE, restricted under the setup that h naught mu equal to a null vector. This of course will be the same procedure would be followed if we have, instead of this null vector, any other specified vector mu naught to be the null hypothesis point. Now in order to find out the restricted MLE, we will have to look at the restricted likelihood. The restricted likelihood at the restricted likelihood would be actually L naught sigma given x. So this is going to be equal to the constant 2 pi to the power minus mn by 2 remains as it is. Then we will have determinant of sigma, all right, to the power minus n by 2. We will have e to the power minus half trace of that sigma inverse A, trace of sigma inverse A. This what I'll do is I'll take this minus half, this trace of sigma inverse A. Let me first write it, this trace of sigma inverse A, this minus n by 2, and then x bar minus mu transpose sigma inverse. Now under the restriction that h naught mu equal to mu naught, that mu is a null vector, and hence what we'll be having here is just x bar transpose sigma inverse x bar. So we can write this in this form, that 2 pi to the power minus mn by 2 determinant of sigma to the power minus n by 2. Then we will have e to the power, if we take this minus half outside. Now note that we can put a trace out here. I'll do this calculation once more. This trace of sigma inverse A minus n by 2. Now this is a scalar quantity, and hence this quantity itself, I can write trace of this term, and once I write trace of this x transpose sigma inverse x, then we can use the fact that trace A equal to trace of AB equal to trace of BA, and then take this x bar on this side using the trace result, and then we will have this as trace of sigma inverse x bar transpose. So we will have this term in a compact form as following, which would help us in order to get to the maximum likelihood estimator by using the same logic as what we had used in order to get to the maximum likelihood estimator for the unrestricted setup. This will be minus half trace of sigma inverse. The entire term is common, so we will have that A plus, now this minus half trace sigma inverse is out now, then we will have n times x bar transpose as this particular matrix. We can write this as 2 pi to the power minus mn by 2 determinant of sigma to the power minus n by 2 and e to the power minus half trace of sigma inverse of a matrix, say, which is equal to B, where B is nothing but the matrix which is this one, where we have this B matrix to be given by A plus n times x bar transpose. Now note that this form that we have here is similar in nature to the form which we had to encounter in order to find out the unrestricted maximum likelihood estimator in case of a multivariate normal distribution. When we had unrestricted setup, then we had to find out the maximum of such a similar quantity with A replaced by just this B, with this B just replaced by this A. Now the maximum likelihood estimator of sigma in such a situation was 1 upon n A. By using the same logic, by analogy actually, what we can say is that from this expression here, if I name this equation as 1, then the maximum likelihood estimator of sigma in the restricted setup would just be given by 1 upon n B. So we will have this one implies, using the same logic as that used in order to find out the maximum likelihood estimator of sigma in the unrestricted setup, what we can say is that the MLE of sigma under the restriction, under restricted setup, is going to be given by sigma hat r, say restricted, that's equal to 1 upon n times B. And what is that equal to? Let us plug back what B was equal to. So it was equal to A plus n times, it's in the random variable form, x bar transpose, so that this is equal to just 1 upon n A plus x bar transpose. So this is the restricted maximum likelihood estimator, and this is the only maximum likelihood estimator over which we are going to optimize, we are going to maximize rather, because mu is given as mu naught. So this would imply that the other part which is required, which is a supremum under script theta naught, under script theta naught mu is given as mu naught, and we have to find out the supremum of the likelihood L mu sigma at the point mu equal to mu naught, so that we will just be using this in place of the previous matrix there, so that this is thus equal to, the constant remains as it is, 2 pi to the power minus mn by 2. Determinant of sigma would be determinant of this quantity now, n inverse A plus x bar transpose whole raised to the power minus n by 2, and then we will have e to the power minus half. Let us see what that was equal to. So this was the restricted likelihood. So if we plug in here in place of sigma this quantity, what we'll be having is this as 1 upon this sigma inverse as n times B inverse, and thus this would just once again be equal to the type of term that what we have. This is going to be n times trace of Im, and this thus would be equal to 2 pi to the power minus mn by 2. We can even take this n inverse outside, so we will have a term m here. N is basically taken out in order to have a similar expression as to that what we had for the unrestricted maximized likelihood. So this will be an n raised to the power mn by 2, and that leaves us with this a plus n times x bar. Now this x bar is going to be small x bar because we have got the data out here. So we will have this written as small x bar transpose, and similarly this would be the small x bar because this is in the likelihood function, x bar transpose whole raised to the power minus n by 2, and then we will have e to the power, this is going to give us m times m. So this is minus mn by 2, right? Now we have both these parts which are required. So this is, say, star 1, this sits in the denominator of the likelihood ratio. If this is given star 1 number, then this is the other expression. This entire expression is what we would require in the numerator of the likelihood ratio. So this would imply that this lambda, which was given by supremum under script theta naught of L mu sigma, this divided by the supremum, I think I should just write this in the center. So this lambda, the likelihood ratio, is given by this term here, which is supremum over this. So this is the supremum under the unrestricted setup, and this is the supremum under the restricted setup. So this, thus, using star 1 and star 2, we can straight away write what is this using star 1, which was this term here, and star 2 equation, which was the restricted supremum. What we get is this form of lambda, which is under the restriction, it's 2 pi to the power minus mn by 2, n to the power mn by 2. Then we have this determinant of, what was it? Determinant of a plus n times x bar transpose whole raised to the power minus n by 2. So a plus n times x bar transpose whole raised to the power minus n by 2, and then we had e to the power minus mn by 2. And in the denominator we have that star 1 expression. The star 1 expression, remember, had a similar constant. These constants are exactly the same, and if we look back at what was star 1, in the star 1 I just missed out this term here. This term was sitting here, so this term would come out here. So we will have this as determinant of a to the power minus n by 2 as well. So this term is this term comes in because this e to the power, this term is here. So we'll have this as 2 pi to the power minus mn by 2. Then we have n to the power mn by 2, determinant of a to the power minus n by 2, and e to the power minus mn by 2. So that is the correct expression of this star 1. This term comes down here. So what we will be having here is a determinant of a to the power minus n by 2, and then we will have e to the power minus mn by 2 term here. So a lot of terms actually cancel out. This term cancels out, this term cancels out with this one, this term cancels out with this one. So what we have is this simple form that lambda to the power 2 by n is going to be equal to, let's flip this two terms, this will be determinant of a this divided by determinant of A plus n times x bar transpose, the determinant of this term here, in just this form. So we will use this form. This is the likelihood ratio lambda raised to the power 2 by n, that is equal to determinant of A divided by determinant of A plus n times x bar transpose. So we will look at in the next lecture. We will start with this particular form and see what is the correspondence of this likelihood ratio lambda and that of the Hoteling's t-square distribution. Thank you.